Hello guys, welcome on Tesla Adventures. In this video, today we are going to discuss further about intrinsic semiconductors. So intrinsic semiconductors are the purest form of semiconductors in which there is no doping. For example, if we take a crystal of silicon or germanium, we can say that a crystal of silicon or a crystal of germanium is the purest form of semiconductor, and it is also called as uh, intrinsic semiconductors. Generally, the elements of group 14 in the periodic table, which are germanium, silicon, and carbon, are the intrinsic semiconductors, and they shows the properties of intrinsic semiconductors. And let us take an example of, let's suppose, silicon crystal. You can see, and in this group 14 elements, the outermost shell of each element contains only 4 electrons. So this 4 electrons are making the bonds with the other silicon atoms from all the 4 sides, and this is how the crystal is formed. So this is the scenario shown at 0 Kelvin, in which all of the electrons are bonded with the covalent bonds and none of the electron is free. So we can say that at 0 Kelvin all the electrons are in the valence band, and the conduction band is empty. But at room temperature in which we exist, at room temperature the electrons have sufficient amount of kinetic energy so that they becomes free, and they break their bond and they jump into the conduction band. So this is the scenario at the room temperature. So at room temperature, some of the electrons are free, and they creates a hole in the valence band. Now, when we apply some electric field on this crystal, then we would see that the electrons will drift in the reverse direction of electric field, because we know that electron is a negative charge, and the force, electrostatic force acting on the negative charge, is in the opposite direction of electric field. So electrons are drifting in the backward direction, and therefore the direction of current due to these electrons is in the forward direction, i.e. Okay, and there is another type of motion of electrons. Initially, we were talking about the free electrons which are drifting in the reverse direction, but there is a motion of bonded electrons also, and this is called as bond to bond transfer. So you can see that when this hole is formed, this hole is a vacancy of the electron which is now free, which was earlier at this position, but now it is free. So it has created a vacancy here, and to fill this vacancy, this electron jumps to this vacancy inside the bond. So this is bond to bond transfer, and then this vacancy will be created at this position, and then this position will be fulfilled by the electron of this one, and now vacancy will be created in this position. So in this way, these electrons will jump from bond to bond, and their motion, the motion of bonded electrons, will be represented by the holes. So in intrinsic semiconductors, or in extrinsic also, the charge carriers are of two types. One is the electron and one is the hole. And when we are talking about the electrons, we are actually referring the free electrons, and when we are talking about the holes, we are actually referring the bonded electrons which are transferring from bond to bond. Now the current of the free electrons and holes will be in the same direction, because obviously holes are moving in this direction, and these holes can be regarded as the positive charge, and they can be considered as protons. So these holes represent actually the motion of bonded electrons, and the free electrons represents the motion of this electron current represents the motion of the free electrons. And in any semiconductor, in the presence of some electric field, the net current would be the sum of IE and IH. And it is very obvious that at room temperature the number of free electrons and number of holes would be same in intrinsic semiconductors, due to the fact that these holes are formed by jumping of the electrons. So if n number of electrons jumps from valence band to conduction band, then n number of holes will be formed in valence band. Now, forbidden energy gap of silicon is 1.1 eV, and for germanium it is zero point 0.7 eV. Hence, we can say that it is easier in germanium for electrons to jump from valence band to conduction band, and hence in germanium more number of electrons are free and there are more number of holes in the valence band. So we can say that the conductivity of germanium at room temperature is better than the conductivity of silicon at room temperature. Now, as we increase the temperature of semiconductors, its conductivity increases and the resistivity decreases with the temperature, and therefore the temperature coefficient of resistance of semiconductors is negative. This we have already discussed in the previous video, but again let me remind you that there are two effects in the semiconductor on increasing the temperature. The first one is the Joule's heating effect, in which when we increase the temperature, electrons gain sufficient amount of kinetic energy and they run here and there, due to which their collision becomes more frequent and they start to lose their kinetic energy frequently, and they experiences some hindrance in the motion, and that is called as resistance of the conductor. But there is another effect, which is effect 2, in which more and more electrons break their bonds and jumps from the valence band to the conduction band. And as one electron jumps from valence band to conduction band, it creates two charge carriers. One is the electron itself and other one is the hole in the valence band. So the conductivity becomes multiple times when we increase the temperature, and therefore the bigger effect is the effect 2, in which conductivity increases. So cumulatively we can say that on increasing the temperature of the semiconductor, intrinsic semiconductor, the conductivity of the conductor increases, semiconductor increases. Now let us talk about the calculations of current flow in the semiconductor. So there is a piece of intrinsic semiconductors, you can see, and we have applied a battery in this intrinsic semiconductor, and you can see that obviously holes behaves like positive charges, and therefore hole will run away from this plus terminal and they will go like that towards negative terminal, and electron will be moving towards the positive terminal of the battery like that. Okay, so we can say that the electronic current will be flowing in this direction and hole current will be also flowing in this direction. Okay, so this will be the current, and we can say that the total current flowing in this wire will be the sum of current of electron and hole, and the number of electrons per unit volume, which is the Ne, which is number of electrons per unit volume, and number of holes per unit volume, it is Nh. These will be equal because we know that number of electrons and holes in intrinsic semiconductors are equal. So we can say that these two are equal, and these are also referred as intrinsic concentration. And if I talk about the current current flowing due to electrons, then according to the current electricity, we know that I is equal to NeVd. So this I electronic current will be Ne, which is the number of electron density or number of electrons per unit volume, free electrons, and A is the area of cross section of the conductor, E is the electronic charge, and V is the drift velocity. In the same way, IH will be NH/AeVH, where NH is the number of holes per unit volume, which is equal to the number of electrons per unit volume, although, and VH is the drift velocity of holes. Now as we have discussed already, that holes is nothing but holes represents the motion of bonded electrons, and bonded electrons are not free. So therefore we can say that the drift velocity of the free electrons will be more than the drift velocity of the holes. So this is the fact. And obviously, therefore, we can say that in the presence of same electric field, IE, electronic current, will be greater than the whole current in the intrinsic semiconductors. Okay, and I total will be the sum of these two currents. Now, if we talk about the current density J, so it is I by A. So I by A will be E times of NeVe plus NhVH, and the drift velocity is mobility into electric field. This mu represents the mobility. And we also know the microscopic form of Ohm's law, that J is equal to sigma E. So we can write down this J as sigma E, and sigma is E times of this. So sigma is E by E into this one. And this mobility of electron is VE, drift velocity of electron upon electric field, and mobility of holes is drift velocity of holes upon electric field. And due to the fact that drift velocity of electrons is greater than the drift velocity of holes, so we can say that mobility of free electrons is greater than the mobility of holes. Okay, and the sigma, the resistivity is 1 upon conductivity, so rho is 1 by sigma. So this was the complete analysis of intrinsic semiconductors, and in the next video I'll be bringing the complete detailed analysis of extrinsic semiconductors. And as you have heard that the types of extrinsic semiconductors is p type and n type, so we'll be discussing the p type and n type semiconductors separately. Thank you.